linear programming, and then tomorrow we'll look at the word problem applications. So today, really, you're going to see that they're more inequality looking, not pertaining to specific word problems. Tomorrow we'll pull in the word problem applications. So today we do it without, so you can kind of get an idea as to what we're looking at. And then tomorrow we'll pull in the word problems. You have a couple problems in your homework, and then there's a couple problems on a worksheet as well. So I think you've got 10 problems tonight. I believe 7 or 8 of them are graphing. So this part here is kind of like an extra addendum added to section 3.3. And our goal is to use our inequalities to get a region that'll help us find a solution to our overall problem. So it says, well, graph systems of inequalities, use these graphs to find max and min values. So we're going to be using the graph to see if we can find a max or a min. Our end goal would be to answer some type of question that is within the word problem. So linear programming says, represents the constraints on the variable with a system of linear inequalities. The goal is to find the max and min values. So what would give us a maximum profit? What would give us a minimum cost? A constraint is a restriction on a variable. We will use constraints throughout the year. And sometimes a constraint, when we did piecewise functions, is written as an inequality. So a constraint and a restriction, those would be two good words to kind of use, good synonyms. A constraint is a restriction. And when you restrict something, you write it as an inequality. So x is greater than or equal to 0 is a restriction. All of your x values must be positive. So you're restricting x to a certain value. The feasible region is that overlapping region or the overlapping area of all of our inequalities. And now, in most cases, it will be an actual shape. So it's going to have some kind of boundaries, and those boundaries will create a shape for us. So a constraint is a restriction on x or y, on the variable, usually written as an inequality. When we graph our inequalities, we're going to end up having this region. And the region is where all of our inequalities are meeting. And that's the area that we're shading. But now it's going to be a bounded region instead of just 2 lines and the area kind of going forever as long as our graphs exist. So the first question we're going to have to draw in here. So it says find the maximum and minimum values of the objective function for the given feasible region. So we're going to draw a little bit of a graph here. So we'll start at the point 1, 1. And we're going to make a quadrilateral. So I just picked some points. So we have a point at 1, 1, 1, 5, 4, 4, and then 5, 1. So if I were to graph 4 inequalities, this could be what my graph would look like. So this is called a feasible region. In the first couple of questions in the book, I think the first 3, you are given a graph. You don't have to graph it. The graph is already given for you. And you'll be asked to find the minimum and the maximum value of the objective function. So the objective function is this equation right here. That equation gives us the goal of the problem. So in this case, C would probably represent cost. So if I want to come up with a minimum cost so that I can make a product that is going to cost me the least amount of money, I would look at the graph, the feasible region, and try and decide which one of those values, how many products will we make so that we have a minimum cost. So the way you find the max and the min is to make a table of values, but instead of having a table of x and y, you're actually using the x and the y as your coordinate. And then on the other side is our objective function, or our cost function, our profit function. It depends on what we're trying to solve. So to figure out if you have a maximum or minimum value and where that occurs, you're going to take your corner points. It's called the corner point principle. So you take how many corner points you have, and a corner point is known also as a vertice. Where are your two lines meeting? So wherever your two lines meet, that creates a point, a corner point, or a vertex. So we're going to take that corner point, all four of them in this case, and list them in our chart. And then see which one gives us a maximum objective function and see which ordered pair gives us a minimum. The max and the min will always occur on the corner points. The middle values in the middle of the graph would occur in between the max and min. So your max and mins will always be at one of the quarter points. If it's in the middle, then it's going to be in the middle of our two values. So plug in those two values, see if you can find a max and a min. So you're just plugging in the ordered pair for each corner point or each vertex that you get. So Michael, the first one, what would our objective function be? 5 and then 13, 20, and 17. So it asked for the minimum and the maximum values of the objective function. So our minimum occurs at 1, 1, and its value is 5. That 5 might represent $500, $5,000, $500,000. So it will represent something. And then our maximum occurs at 4, 4, and that value would be 20. Again, whatever the 20 represents. Tomorrow we'll have applications to it, yes. These points here, it'll be wherever our two lines are meeting. So wherever the two lines intersect is where we place our points. I just graphed this one, so I just made my own graph. So in your homework tonight, you'll already have a graph given to you that already has the value, like the picture shown. So I just made this one up. Other questions? So if you look at the next page, there are two different problems for example 2. And it wants you to graph the feasible region. So now I should have this shape that is occurring from graphing our information. So feasible region, the shape that kind of is created once you graph our restrictions or inequalities. And then it says to label each vertex. So wherever our two lines meet, we'll be labeling those points or the ordered pairs. So the first thing, this graph, you just have a big graph. So you can draw an XY axis in the middle of it. So now I have an XY axis. And the first part says we want to look at x being greater than or equal to 0 and y being greater or equal to 0, which were those two questions that pertain to our warm-up. So x being greater than or equal to 0. When you have x, that is our vertical line. So I now have a vertical line. Greater than or equal to 0 means I need all of the x values that are positive. So I'm going to shade in that direction. The second one says y is greater than or equal to 0. Y is our horizontal line. So that is the horizontal line because the slope is 0. And that would be on the x-axis. Greater than or equal to means I'm shading above. So just by graphing those two, I know my answer should be in the first quadrant. So that's where our feasible region should be located. Based off of the first two restrictions, my answer is going to be in the positive quadrant, that first quadrant. The third part says x plus y is less than or equal to 6. Chris, what would that inequality be that we're graphing?
Y is less than or equal to negative x plus 6.
Yeah. So now we have a line that is going to have a slope, a decreasing slope. So going up to 6. And then down 1, right 1. And again, these say greater than or equal to, so right now we have all solid lines. Less than or equal to, greater than or equal to, all solid lines. This one is less than means below. So now my answer is below. And if I would stop, right now I'd have a triangular region. But there is one final inequality, and that final inequality says 12x plus 6y is less than or equal to 48. So Peter, what would that fourth inequality look like if we solve for y? So our final inequality, y is less than or equal to negative 2x, and then plus 8. So that one goes up to 8. And now we're moving down to right 1. If you have a point where they meet, I kind of bold that point. We get a little bigger because that's going to be an important location for us. That'll contain one of our vertices. So this one also says less than or equal to. I'm going to use that information that I already have to shade in my final solution. So it has to be above the x-axis, to the right of the y-axis, and then below the two diagonal lines. So now that I actually have a system of inequalities that creates this feasible region, the last thing for you to do is to get those 4 vertices. And a vertex occurs where your two lines intersect. So they kind of create the boundaries for your graph. So you can label them on the graph, you can list them below the graph. So Sadie, we have one at 0, 0. A second one at yeah, 4, 0. So that one's on the x-axis. Where else, Sadie? Yep, 0, 6. And then there's one final one in the middle. Josh, what's that one at? 2, 4, yeah, that one's at 2, 4. So if we had an objective function, then I would take those 4 points, the 4 vertices, and plug them into our objective function, either to find a maximum of something or a minimum of something. Questions? So that is linear programming without the application, without the word problem part. But a linear programming kind of takes your restrictions and bounds it to a specific region of the graph. If you look at example 2, example 2 is a little different because it's using letters C and D. How do you know which one represents X and which one represents Y? And there really is a reason as to which one goes with which. Dimitri?
Alphabetical order?
Yeah, it's always alphabetical order. So your independent variable is first in the alphabet. X is first, it goes before Y. So that means our C is our x-axis and our D is the y-axis. Nice job, Dimitri. So alphabetically, you don't just pick one, really alphabetical order. So the C would be the independent variable, or the x-axis, the D would be the dependent variable, or the y-axis. The first inequality is called a compound inequality. So I have the variable in between 2 numbers. How do you graph that? 1 is less than or equal to C is less than or equal to 4. Josh, how do you graph that? Yeah, think of it as 2 separate inequalities. So if you start in the middle, and if you would prefer to see that as X, write it as X. So if you don't like seeing a C there, change it to an X. But if I start in the middle and read to the left, this is saying C is greater than or equal to 1. And then go back to the middle and read to the right, C is less than or equal to 4. So the compound inequality actually creates 2 separate inequalities. So going to my X or C, depending how you're thinking about it, we're going to the value of 1 on the C axis, and then we are making a vertical line. Remember, when it's X by itself, when your independent variable is by itself, it's a vertical line. The slope is undefined. And then on my C axis, I'm moving over to 4 and drawing another vertical line at the value of 4. Because the inequality, the variable C, was in between those 2 compound inequalities, those 2 numbers, my solution has to be in between those 2 vertical lines. So X or C is in between 1 and 4, so my solution has to be in between 1 and 4. In between the 2 vertical lines. So the second inequality says C plus D is less than or equal to 14. If I solve that in terms of D, D is less than or equal to negative C plus 14. I'm going to have to go up a couple extra. We could have moved our axis down as well, but that's all right. So up to 14, and then as carefully as you can, down 1, right 1. Less than or equal to means below that line, so we're below this line here. So in between the red lines, I'm below my diagonal line. And again, where they are meeting, where my vertical line is meeting with that diagonal line that I just drew, those 2 points are important. The last inequality says D is greater than or equal to 2C. What's the y-intercept of the fourth inequality there? The 0, yeah. So that starts at 0. And then Chris, its slope is up 2, right 1. And wherever they're meeting with those vertical lines, those are the important points. That's the only, or the final inequality that we're graphing, and it says greater than or equal to. So I need to go above the line. So my solution needs to be in between the red lines. Mine are red, but in between those vertical lines. Above the lower diagonal line, below the upper. What shape does this make? A trapezoid, going back to wonderful geometry. So list the 4 ordered pairs. Where are they connecting? So with the vertical lines, where are your 2 diagonal lines intersecting with the vertical lines? 2 of them intersect with the line of x value of 1, and then the other 2 intersect with our x value of 4. Yeah, so one of them intersects at 1, 2. Where's another one intersect? 113, and then 4 and 4 and, say it again, 8. Questions? So your homework is, part of it's in the book on page 176. It's the top 6 problems. The first 3 give you a graph that's already there, and you are asked to find the maximum and minimum using the vertices of the graph. And then the next 3 you'll be actually graphing. The warm-up that I gave you at the beginning of class, the bottom 4 problems of that warm-up are the other part of your homework. So the warm-up contains 4 graphing problems, and those 4 graphing problems are the other part of your homework tonight. So 6 questions in the book, 4 questions at the bottom of that worksheet. So tomorrow we'll pull in the application part, and it'll kind of make a little more sense once you deal with the application. 5 and 6 from the book. Anybody interested in graphing 5 or 6 from the book for tomorrow?